Okay, so this lesson is to cover both 2.2 and 2.3. We're not doing all of 2.2. We're only going to do part of it. Inductive and deductive reasoning is the title for 2.2. You don't really need to know the definitions of inductive and deductive. I'll mention them briefly. But the main two things that we need from 2.2 are the definitions of conjecture and counterexample. We talked a little bit about counterexample in the last lesson. So a conjecture is an unproven statement that is based on observations. You use inductive reasoning when you find a pattern in specific cases, and then write a conjecture for the general case. So again, the key word that we're focusing on here is conjecture. So if you're doing it in your index cards, I didn't even put inductive reasoning and deductive reasoning on the index cards. We're just focused on conjecture and counterexample. So again, important thing, in order to make a conjecture, it is you're observing what's happening, you're making a prediction about what else is going to happen, and again, that's your conjecture. So if you think about science, conjecture is kind of like a hypothesis in science. So in the first example, describe how to sketch the fourth figure in the pattern, then sketch the fourth figure. Well, on here, we have three figures. So we have to look at what's happening in these figures. Well, first off, the first diagram has two actual spaces. The second one has 4 spaces. The third one has a total of 6 spaces. So what's actually happening? Well, if we look at each figure, so this is the first figure, this one had 2. The number of spaces the circle is divided into is twice the number of the figure. On this one, figure 2, twice 2 is 4. So again, twice the number of the figure. On the last one, figure 3 had 6 spaces, because again, twice figure 3. So then figure 4, we can make a conjecture for, since we know that we have double the number of spaces for each figure. Figure 4 will now be 4 times 2, so it'd be 8. So we're going to divide a circle into eighths. And then we should also look at where that shaded region is, because in each time we have a shaded region that always falls just above the horizontal line on the left side of the figure. So we're going to do the same shading on figure 4. And this is what we believe figure 4 is going to look like. Again, we're making this guess based on the pattern that we saw. So we made a conjecture as to what this figure is going to look like. Now, a counterexample. Talked a little bit about that in the last lesson. To show that a conjecture is true, you must show that it's true for all cases. You can show that a conjecture is false, however, by finding just one counterexample. A counterexample is a specific case for which the conjecture is false. So it's an example that counters the claim. So if you can find one false statement, the entire conjecture is false. So here's an example with counterexample. A student makes the following conjecture about the sum of 2 numbers. Find a counterexample to disprove the student's conjecture. So the conjecture is the sum of 2 numbers is always more than the greater number. Well, the sum of 2 numbers is always more than the greater number. That's not always true, because in math we have positives and negatives. So to find a counterexample, you need to find a sum that is less than the greater number. So on here, let's see. Well, they chose to do -2 and -3, which gives us a total of -5. The bigger number here was actually, it's going to be the -2 is the biggest number when we put them in order on a number line. So -2 is the biggest number, and the sum, -5, is actually the smallest number here. So again, this is just one counterexample, but we only need one counterexample to prove that it's wrong. So since -2 is going to be greater than -5, it is false. All right, and that's it for 2.2. That's all we're doing from 2.2. So 2.3, this section, we're talking about postulates and diagrams. Now, there are lots of postulates. All right. So there's only one definition in this section, line perpendicular to a plane, which I'm not even having you include in your index cards. So you may have noticed that this section was skipped altogether on the list of vocab. We already defined what a perpendicular line was back in 2.1. You don't really have to define this a separate time. It's the same definition, except instead of being perpendicular to a line, it's perpendicular to a plane. Now, we're going to look at lots of postulates. We need to be able to memorize these postulates. I highly recommend in your textbooks, when you get a chance in the classroom, to rip out the pages that are in the back now. There is, in the back, there's like the glossary, there's the answers to the odd problems, and then at the very end, there's A81 through A92. It has all the postulates and all the theorems that we're going to be looking at, as well as a reference sheet with all the formulas that we're going to be using throughout the year, not just the formulas that are on the reference sheet for the EOC. So I would recommend ripping those out, hole punching them, putting them in a binder, all right, so that you have them all year long. Again, you can't use those on a test, but you have them in one place to study and to refer back to. So now, identifying a postulate. So first off, what is a postulate? A postulate is something that is accepted as true. We did that definition back in the first chapter. So on here, we are going to have 7 postulates involving points, lines, and planes. The first one, the 2-point postulate. Through any 2 points, there exists exactly one line. So this is an important postulate because it allows us to actually draw a line anytime we have 2 points. So they have the example over there off to the side. Through points A and B, there's exactly one line, line L. No matter what, if we started with 2 points, there's only one way that you could draw that line and have it go through those points. On the next one, 2.2, line point postulate. And I should mention, you don't actually have to memorize the numbers. So 2.2, you don't have to memorize that. Again, the names you should know and what they're talking about. Line point postulate. A line contains at least 2 points. So again, in order to name a line, we had to have 2 points. So a line contains at least 2 points. Again, these are things that are accepted as true. A lot of times they're going to seem like, hey, that's common sense. Why do we even need to know that? Because it's a rule, and we're going to have to use these rules when doing our proofs later on to explain how we are able to do something. Again, it's very important that you know the why and not just, oh yeah, that's correct. Again, you have to be able to explain it. That's the whole idea behind a proof, which is what we're getting to. So yes, you do need to memorize the postulates and theorems as we go. I'm not requiring you to do index cards for them. If you want to make separate flashcards for them, you're more than welcome to, but you need to know them in order to use them in proofs. So like I said, I'd recommend ripping out those pages from the back so you have them all in one place so that you can refer back to them. If you forget what one is, you can easily find it. All right, postulate 2.3, line intersection postulate. If 2 lines intersect, then their intersection is exactly 1 point. So in the example, we have 2 lines that are intersecting. And in this example, lines M and N intersect at point C. The intersection of line M and N is point C. There's only 1 point. You can't have 2 lines intersect at 2 different points. And you learn this property actually in algebra as well, when you talked about linear equations. When you have linear equations, they can only intersect at 1 point because, again, linear equations are lines. So if 2 lines intersect, then their intersection is exactly 1 point. Now, are lines always going to intersect? No. We'll talk about parallel lines later on. We'll talk about skew lines later on. So they're not always going to intersect. But if they do intersect, then their intersection is exactly 1 point. On 2.3, oh, sorry, that was 2.3. 2.4, 3-point postulate. So very similar to the 2-point postulate. 2-point postulate dealt with the line. Now 3-point postulate deals with a plane. Through any 3 non-collinear points, there exists exactly 1 plane. So again, we have the diagram. We have the 3 points, points D, E, and F. D, E, and F are on that plane. That plane is labeled plane R. So through points D, E, and F, there's exactly one plane, plane R. Plane R contains at least 3 non-collinear points. So the opposite of that, again, a plane point postulate. A plane contains at least 3 non-collinear points. It's essentially almost the converse of what that first statement was, right? The first one saying, if we have 3 points, we have a plane. The second one saying, if we have a plane, then we have 3 points. So again, it's like what we're doing the past couple days with 2-1. It's just the converse of that original statement. All right. Clear that. So on the next one, 2.6, plane line postulate. If 2 points lie in a plane, then the line containing them lies on a plane. So again, it's just an extension of that first 2-point postulate. So now we have, if we had 2 points on a plane, then the line that they're on will be on that plane. So in the example, we have the points D, E, and F again on plane R. No matter which 2 points you pick, if you draw a line through any 2 points there, so they drew one through D and E, that line now has to be on that plane. On 2.7, plane intersection postulate. If 2 planes intersect, then their intersection is a line. So we've talked about this one already. Early in the year, we didn't have a name for it yet, but now we do. It's plane intersection postulate. And there are some postulates that are going to be more useful than others as we go through the year, but it's helpful to know all of them. All right. State the postulate illustrated by the diagram. So on A, it says if, and it's showing 2 lines intersect, then, and it has a red dot on that point where they're intersecting. So if 2 lines intersect, then they intersect at a point. So that was our line intersection postulate. If 2 lines intersect, then their intersection is exactly 1 point. Again, notice when I said it before even saying the name of it. It's okay if you quote the exact postulate instead of saying the name sometimes. Some books don't even give some of these postulates names. This book tends to give almost every postulate a name, but some of the earlier books that I used just did the postulate, and that's fine for some of these more basic ones. The second one, we have 2 planes intersecting, and then it says then, and it shows a line. So if 2 planes intersect, then their intersection is a line. And that's plane intersection postulate. Again, these names aren't rocket science. They're pretty straightforward. What happened? We had 2 lines intersecting. So what's the postulate? Line intersection postulate. We had 2 planes intersecting. What's the postulate? Plane intersection postulate. Again, they make them pretty generic and easy to understand. Even if you forget the names of it, you could almost guess at some of these. Then on example 2, identifying postulate from a diagram. Use the diagram to write examples of plane point postulate and plane line postulate. So on here, we have 2 planes that are intersecting. We have, again, the first one, plane point postulate. So in plane point postulate, it says that a plane contains at least 3 non-collinear points. So pick a plane that has points showing on it. We had B, A, and C. Those are the only 3 points that we have, so we're going to have to use those 3 points. So A, B, and C. And those are on plane N. So we can say plane P contains at least 3 non-collinear points, A, B, and C. So again, those 3 points were on that plane, and that's plane point postulate. The second one, plane line postulate. Plane line postulate said if 2 points lie in a plane, then the line containing them lies in the plane. So here we have a couple different points. Now they only have 1 line drawn. Currently it's BA. So we're going to use those 2. We have B and A. We have a line drawn on them. They're both on plane P. So we have that line going through points A and B, and that line N, must fall on plane P. All right, so point A and point B lie in plane P. So line N containing points A and B also lie on plane P. Now, I think I did make a mistake a few seconds ago when I was talking about plane point postulate. I think I accidentally called this plane plane N. Again, N was a lowercase letter, so the name of this plane is actually plane P. So I just want to make sure I corrected myself. All right, example 3, sketching a diagram. So now this one says sketch a diagram showing line TV intersecting segment PQ at point W so that segment TW is congruent to segment WV. All right. So first thing we need to draw is draw a line TV and label the points. So there's TV. We're going to label the points. Once you have them labeled, then we need to have the other line, line segment PQ, drawn so that it goes through point W. So point W is going to be equal distance from those 2 points. So we're going to draw point W, make it the midpoint. So that's equal distance away. I mark them as congruent so that we can clearly tell that they are congruent, because again, we can't assume. And then once we have point W, we can draw that line segment through point W. So PQ goes through PW. So PQ goes through point W on line TV. And again, that line is a line segment. So we have endpoints, but it doesn't continue. Now, they showed another example over here off to the side. So there's more than one way to sketch that. And that's important to understand. There's not always going to be one way to show this. A lot of times with our problems that we're going to be doing, it's important to draw a diagram, but not everybody's diagram is going to look the same. What's important is that we draw an accurate diagram that works, and then we are able to label it so it helps us solve problems. All right. This is the only definition. And like I said, I did not make an index card for this one because I thought it was pretty self-explanatory. If we already did the definition of perpendicular, then this is a line perpendicular to a plane. So a line perpendicular to a plane if and only if the line intersects the plane in a point and is perpendicular to every line in the plane that intersects it at that point. In a diagram, a line perpendicular to a plane must be marked with a right angle symbol as shown. So just like when we have perpendicular lines, we're still using our right angle symbol to show that it is perpendicular to that plane. Again, it's kind of self-explanatory. In fact, this definition is a little wordy. So I think it's more confusing than the actual idea of a line being perpendicular to a plane. The one thing that I do think is important in here is to show how they actually used something from the last section. They talked about if and only if here. Since we're doing a definition, we can do that definition as a biconditional statement and use the words if and only if. Anytime we have a definition, it can be written in that if and only if format. We can also write any of our definitions in just as a regular conditional statement as well. All right. Example 4, which of the following statements cannot be assumed from the diagram? So we have points A, B, and F are collinear. So if we look at A, B, and F, they're all on the same line. So they are collinear. So that's acceptable. Points E, B, and D. Actually, I think it shows the steps here. So let me go through them. A, B, F, that's from the first one. They're on the same line. So they are collinear. Then we have points E, B, and D. It says they are collinear. Well, our postulate said that any 2 points on a plane can be collinear. Here it's showing 3 points on a plane, and it doesn't have a line drawn through them. So we don't really know that that one's collinear. So that one, since there's no line drawn there, we cannot assume that those are collinear. In order to know for sure, they would have had to have shown a line through them. Look at the next one. We have line AB is perpendicular to plane S. Line AB does look perpendicular, and to make sure that we know it is perpendicular, we have the right angle symbol with the plane so that we know it actually is perpendicular with that plane. Since they show that right angle symbol, we know it is perpendicular to the plane. Now, the other line, line CD, is perpendicular to plane T. Again, it looks like it could be. All right. It's a little bit hard to tell because this one's going back at an angle. This was going back at an opposite angle. So it looks like it really could be perpendicular. However, since they don't have a right angle symbol, we cannot assume that it is perpendicular. So that one is also incorrect. So again, those two things cannot be assumed. And then the last statement, line AF intersects line BC at point B. Well, it shows them both intersecting at that same point. In fact, they share that point in common. So we can definitely say that. So the only two that we cannot assume are the two that we already mentioned. We cannot assume the second statement because there's no line drawn, and we can't assume the fourth statement because there's no right angle symbol. And that's it for 2-3. So again, make sure you get your assignments done for this section, and I will be back on Monday. There are a total of 3 assignments that you should be working on. While I'm out, it was the assignment from 2.1, and then there's 2 parts to the assignment from 2.2 and 2.3. So make sure you get those done. And make sure you also have your vocab words done for 2.2.